Hello guys, welcome on Tesla Adventures. In this video, we are going to discuss the detailed solutions of this mock test which I uploaded yesterday. So section 1 has 6 questions and all of them are single correct one. So in this question number 1, you can see that this is the a wall which has two layers, this and this, and the temperatures of these two ends of the wall is fixed. They are constant. It is constant at temperature T1 and it is constant at temperature T2. This thickness is layers thickness of the layers is x1 and x2, and we have to choose the correct option. We know that the heat as T1 and T3 are constant, so the heat flowing through this will be same, will be Q, and it would be same constant, or I can say that heat current would be constant, and heat current will be equal to dt by dx divided by Ka. This is dx upon Ka is resistance, thermal resistance, and dt by dx is the temperature gradient, which is the slope of this graph. Now obviously dt by dx will be negative due to the fact that as we will move in the forward direction, then temperature will decrease, and it is inversely proportional to K, which means that the material which has greater magnitude of slope will have a smaller value of K. Okay, because if K is small, then dt by dx will be greater in magnitude. So you can see that the greater magnitude of slope is in the second slab. Therefore we can say that the K of second slab would be smaller. So the correct answer would be A. As if K1 is greater than K2, then slope of this graph in first one will be less and in second one would be more. Now we move on the next question. In this question you can see there are two spheres of different materials. Let us draw these two spheres, and material is different. One of the sphere has double radius, so its radius is r and its radius is 2r, and the wall thickness is one with double radius and 1/4 wall thickness of other. So if wall thickness of this is T, then wall thickness of this is 4T. Okay, and they both are being filled with ice. If the time taken for complete melting of the ice in the sphere of larger radius is 25 minutes and of the smaller radius is 16 minutes, then the ratio of thermal conductivities will be. See, we know that the mass of ice would also be different because ice is completely filled and therefore the volume is different inside the sphere, so mass would be also different. Now we know that Q1, the heat required to melt M1 ice, would be M1, which is mass of the ice, will be rho into volume of ice. Let's suppose the volume of this sphere is V, so volume of this ice will be V, and the latent heat of fusion is LF. And the volume of this sphere would be 8V because its radius is twice. So Q2 required for the second sphere would be rho into 8V into LF. This is the heat required. Now we know that the thickness is also different. So the heat will be flowing from outward to inward. So if let us suppose that the thermal resistance is small r, in fact thermal resistance is capital R, so the thermal resistance of first one, A, will be 4T by area, surface area is A, this is 4 by 3 pi r cube, and the surface area is 4 pi r square. So 4t upon a into k1, okay, and rb will be equal to t upon the area of this sphere will be 4a, okay, because radius is twice, so 4a into k2, okay. And we know that the outer temperature and inner temperature for both of them is same, so we can say that dq by dt is equal to delta t by r. So we can say that dq1 by dt upon dq2 by dt will be equal to r2 upon r1, okay. And let us use another page, okay. So you can see that dq1 by dt, q1 is rho vlf. So q1 is let me use this, q1 is equal to rho vlf, and q2 is equal to rho into 8 vlf, rho into 8 vlf, okay. So we can say that dq1 by dt is q1 by t1, and dq2 by dt is q2 by t2. So dq1 by dt upon dq2 by dt will be equal to q1 by q2 upon t2 by into t2 by t1, and this q1 by q2 is equal to 1 by 8, so 1 by 8 into t2 by t1. So t2 of the larger sphere is 25. If the time taken for complete melting of ice in the sphere of larger radius is 25, so t2 is time is 25 in for second one, and for first one this time is 16 minutes. So time will be 25 upon 16. This is the ratio 25 by, this is 64 into 64, okay. So this is the 8 into 16. This is the ratio of dq1 by dt upon dq2 by dt. So this is 25 by 8 into 16, okay. Now you can see that this dq1 by dt is inversely proportional to the radius. So this ratio is r2 by r1, so this is r2 by r1, and we have already calculated r2 by r1, so rb by ra will be equal to, you can see that rb by ra will be equal to k1 upon 16 k2. Check, you can check that. If you divide these two, rb by ra, then it would be k1 upon 16 k2. So this is r2 by r1. So r2 by r1 is equal to k1 upon 16 k2. So cancelling this 16, so k1 by k2 will be equal to 25 upon 8. So the ratio will be 8:25. So the correct answer is D. Now we move on the next question. In this question, you can see that this is the graph between log of theta minus theta naught with time of Newton's law of cooling, and we know that the relation of theta minus theta naught was equal to was an exponential function. If we take the log both sides, then obviously it would be a linear function, and hence we can say that the correct answer will be option 2. now now in this question you can see that there is a rod of length L. So this is a rod of length L, and the area of cross section of the rod is A. The thermal conductivity is variable, and the ends are maintained at different temperatures. So let us imagine that we know that in a steady state heat current would be same. So I will be equal to, let us imagine a small element of width dx, and the resistance of this element, the temperature difference across this small element will be dt. So this is dt. The resistance would be dx upon Ka, where K is alpha T into area. Okay, so you can see that I dx is equal to alpha A T dt, and integration both the sides. So limit of x would be from 0 to L, and limit of t will be from t1 to t2. So I dx will be equal to alpha A and t square by 2. Limit will be from t2 to t1. Obviously we know that this heat current would be positive, so we are taking the mod. Okay, so t2 to t1. So this is IL is equal to alpha A by 2, and this is t1 square minus t2 square. So I will be equal to alpha A by 2 L, and this is t1 square minus t2 square. So the correct answer will be second, in fact D option. Now we move on the next question. In this question you can see there are three very large plates that are placed very close to each other like that, and they are ideal black bodies. The temperature of this plate is 2T and this is 3T, and we have to find out the temperature of the middle plate. We know that obviously this plate will radiate in both direction. This plate will radiate in both direction, but this plate will absorb only this radiation from this plate, and this plate will absorb only this radiation from this plate. So if the surface area of these three plates is same, then we can say that in the steady state the heat absorbed by middle plate, Q power absorbed, so power absorbed by the middle plate will be from these two plates, and it would be sigma into E is 1, A is area of plate, and this is 2T to the power 4 plus sigma A into 3T to the power 4, and power radiated will be equal to sigma into 2A. And now this is due to the fact that this plate would be radiating in both directions obviously, and these two plates will be absorbing these two radiations. So the total area of radiation will be 2A, both side area. So it would be T0 to the power 4. So in a steady state we can say that power absorbed will be equal to power radiated, and therefore sigma A is common. 2T to the power 4 plus 3T to the power 4 will be equal to sigma A into 2 T0 to the power 4. So cancelling this is 16, and this is 81, and this is 97 by 2. So answer would be 97 by 2 to the power 1 by 4T. C option is the correct answer. Now we move on the next question. In this question you can see that there is a single rod of area of cross section A that is used to melt the ice in the box, and this is the heat source. So let us suppose that the resistance of this rod is R. Now this rod is divided into two parts and they are connected in parallel. So this is R by 2 and this is R by 2. So R equivalent will be R by 4. And now the same heat source is used to melt the same amount of ice. So the time taken we have to calculate. So we know that Q by T1 is equal to delta T by R1, which is R in the first case, and Q by T2 will be equal to delta T by R by 4. Okay, so you can divide and you can see that T2 by T1 will be equal to 1 by 4. If you will divide these two, then it would be T2 by T1 and it would be equal to 1 by 4, and therefore T2 will be equal to 1/4 of T1. So correct answer would be B option. Now we move on the next question. In this question, you can see that there is a potentiometer arrangement, and this P is the null point, and which means that when jockey is connected at this point, the Ig will be 0. So we know that no current will be flowing through this branch like that. There is no current through this branch, but a current will be flowing in this branch. I will be it, and it will be same. So there is a current in this circuit because they are making a closed circuit. So this I is simple. This I, you can see that these batteries are in series. So this I is 8 upon 2, which is 4 ampere. What I have done, I have used KVL. This is plus 2 plus 6 minus I into 1 minus I into 1. So current passing through a 6 volt battery is 4 ampere. Current passing through 2 volt battery is 4 ampere. This is correct. VA minus VB. Now this is A and this is B. So if we apply KVL in open loop, so VA minus 4. Now no current is flowing through this one, so we will not consider this, and we are going from top, so it would be minus 2 and plus I into 2, because we are moving in the opposite direction of current, is equal to VB. So VA minus VB will be equal to 6 minus 2I. I is 8, so this is 6. This is 6 minus 4 into 2, 8. So this is minus 2. Let us also reconfirm our answer by going from the downward circuit. So let us again apply the KVL. VA minus 4 and plus 6. This is plus 6 and minus IR. I into 1 is equal to VB. So VA minus VB will be equal to, this is minus 2 plus I. Okay, and in fact, 1 second, this would be 1. So this is I only. So I is 4. So this is 4 and this will be plus 2. So this is it. So I is 4, 4 minus 2 is plus 2. So the correct answer is 2. So the correct options are A, B and C. Now we move on the next question. In this question you can see that these are two capacitors which have same capacity, and this capacitor is being initially charged with some charge Q, and this switch is closed at t is equal to 0. We have to find out the current as a function of time and charge as a function of time. We know that obviously we have done such kind of questions. We know that if at any time, let us use a new page. Let us suppose that at any time this is the circuit and you can see that these plates are isolatedly connected together, and the Q total of these two will be minus Q, and Q total of these two will be plus Q. So we know that this Q total will remain same. So let us suppose that at any time a Q charge is on this plate and a Q of minus Q will be on this plate, because total should be Q. So there will be a negative minus, and here it would be a minus of Q minus Q. And now we can apply the KVL. So you can see that, let us suppose that some current will be flowing. We also know that if initially this is charged and this key is closed, so this would be charging this one, so this plus charge will be flowing like that, so current will be flowing like that. So let us use the appropriate direction of current. So we are applying KVL like that. So this is minus Q by C for this one, and plus Q minus Q by C for this one, and plus IR is equal to 0 for this one. Okay, so this is the equation, and IR will be equal to Q, in fact IRC will be equal to Q, in fact this would be equal to 2Q minus Q. Okay, now you know that what would happen, that initially current was 0, and as soon as switch is closed current will start to flow, and again after infinite long time the current will become 0. Okay, so this will be the case, and as soon as we are closing the switch, current will be appearing in the circuit and it would decay. So therefore we can say that current is decaying, and therefore or we can also say that this charge on the capacitor is getting is flowing from this plate to this plate. So Q, this Q was initially capital Q, but it is now decaying. So we can say that I will be equal to minus of dQ by dt. So this is minus dQ by dt into RC is equal to 2Q minus Q. So dQ upon 2Q minus Q is equal to minus dt by RC. So integrating both the sides, we know that the integration of this would be ln 2Q minus Q divided by 2, and limit will be, and this is minus T by RC. Now the limit of this will be from, initially small q was capital Q, and at any time t is small q, so it would be ln 2Q minus Q and divided by Q. This will be minus 2T by RC. So this is 2Q by Q is equal to C. Let us first of all divide it. So ln 2Q by Q minus 1 is equal to minus 2T by RC, and 2Q by Q is equal to e to the power minus 2T by RC plus 1, and Q will be equal to Q by 2, 1 plus e to the power minus 2T by RC. You can check that initially. Now let us use another plate. Q is equal to Q by 2, and this is 1 plus e to the power minus T by RC. Okay. Now you can see that at t is equal to 0, let us verify the answer. At t is equal to 0, q, this is obviously 1, so q is equal to q, and at t is equal to infinity, so q is equal to q by 2, obviously, because this charge will be equally divided in both of them. So now this charge on capacitor C1 will be q by 2, 1 plus e to the power minus t by RC. This is the correct one. So option B is correct. And charge on capacitor C2. Now charge on C2 will be q minus q. So q minus q will be equal to q minus q by 2 minus e to the power minus t by RC. So this is q by 2 is common, and this is 1 minus e to the power minus t by RC. So this option is also correct. And current in the circuit, I will be equal to minus of dq by dt. So it would be minus of q by 2 into minus 1 by RC e to the power minus t by RC. So this is plus q by 2 RC e to the power minus t by RC. So there would be a 2 also. Okay, 1 second. Yeah. There is a this is e to the power minus 2t by RC. So this is very important to note that there is a 2 here. Okay, there is a 2 here also. So I think that this option will not be correct. This is not correct because there would be a 2, and let us check that 2 also. Yeah, there would be a 2, and therefore it is incorrect. Now option A, when I would differentiate it, there would be a 2 also here. 2. So 2. So cancelling this 2 with 2. So A is also correct. Q by RC e to the power minus 2t by RC. So this is I is equal to Q by RC e to the power minus 2t by RC. And the total heat loss in the process. So heat loss is directly calculated by the formula H is equal to half C1 C2 upon C1 plus C2 into V1 minus V2 का whole square. So H would be equal to half C1 C2 upon C1 plus C2 will be C by 2, and initially V was Q by C, so Q by C whole square. So 1 by 4 Q square by C. So D is also the correct option. So the correct answers are A, C and D. In this question, you can see that there is a micrometer which is galvanometer. Its resistance G is 100 and its Ig is 50 into 10 raised to power minus 6. And we have to convert it into voltmeter of this range and ammeter of this range. So we know that first of all I is Ig, this is G by S plus 1 for ammeter, and for voltmeter V is equal to Ig into G plus R. Okay, now you can verify that by these two formulas, B option and C option would be the correct answer. I can also tell you that if I is 5 milliampere, so this is 5 into 10 raised to power minus 3, and Ig is 5 into 10 raised to power minus 5, G is 100 by S plus 1. So this is 100 is equal to G, this is 100 by S plus 1. So approximately S will be equal to 1 ohm. So C is correct, and similarly B will be the correct option. Now we move on the next question. In this question, you can see that there are two metallic spheres A and B that are made up of same material, and they have got identical surface finish. The sphere A has mass of the sphere is A is 4 times and mass of sphere of B. So both the spheres are heated to the same temperature, and they are placed in a room having lower temperature but thermally insulated from each other, which means that those spheres would not exchange the heat between them, but they will exchange the heat individually with atmosphere. And obviously the first sphere has, let us suppose this is A and this is B. The mass of a sphere is 4 times of B, so obviously this would be the A and this would be the B, and this is RA and this is RB. So mass is proportional to volume if density is same, obviously, and volume is proportional to R cube. So MA by MB is equal to 4, therefore it would be RA cube by RB cube, and RA by RB will be equal to 4 to the power 1 by 3. Now the both spheres are having same material, so E will be same, and they are heated to the same temperature, so T is same. Now ratio of heat loss of A to that of B will be, so first of all, heat loss is the power loss, obviously. So P of A upon P of B will be, we know that P is sigma EAT to the power 4, so it would be area of A into TA to the power 4, and temperature is also same, obviously, so it would be dependent on area only, and this is AB. So area is RA square upon RB square, so it would be RA by square upon RB square would be 4 to the power 2 by 3, and it can be written as 2 to the power 4 by 3. So A is correct option. And ratio of rate of cooling. Now rate of cooling is dT by dt, and that is proportional to area and inversely proportional to mass. Okay, so the ratio of area is 2 to the power 4 by 3. So the ratio of rate of cooling, let's suppose this is R, so this is R, so RA by RB will be AA by AB upon MA by MB, so this is MB by MA. So AA by AB is equal to 2 to the power 4 by 3, so it would be equal to 2 to the power 4 by 3, and MA by MB, MB by MA is 1 by 4, so this is 1 by 4. Okay, so it would be 4 can be written as 2 to the power 2, so it would be equal to 2 to the power 4 by 3 upon 2 to the power 2, so it would be equal to 2 to the power minus 2 by 3. So the correct option will be equal to C. So the correct answers are A and C. Now we move on the next question. In this question, you can see that this is a small part of any circuit, and all the capacitances are equal to 5. Now the first option says that the potential of O can be determined, but that of B can't be determined. See, we have this situation and we need to find out the potential of O. So we clearly observe that we can apply the nodal analysis, But there is a problem that in nodal analysis we need this potential to find out the potential of O. So if VB is not known, then we cannot find out the potential of O. So option A says that potential of O can be determined, but potential of B cannot be determined. So we cannot determine the potential of O without knowing the potential of B. Okay, and similarly, if we see that potential of B and O can't be determined, obviously this is the correct option. If charge on C2 is given, so if the charge on C2 is given, then this potential difference is given, delta V, and delta V will be VO minus VB or VB minus VO. So if this is given to us, then by using nodal analysis we can directly find out the relation between O and B, and we can, if this charge is given, then let's suppose this is Q1. So we will apply the nodal, or let us suppose that this is Q, and we have assumed the potential of O as VO. So we are applying the nodal as VO minus 10 into C3, this is C3 and this is 5, plus VO minus 0 into C4 is 5, plus VO minus plus 10 into C1 is 5, plus this Q. So if this Q is given, then we can find out VO, and if we can find out VO, then obviously we can find out VB, because in that case delta V will be given, and delta V will be equal to Q by C, which is 5. So if charge on capacitor C2 is specified, then potential of both points O and B can be determined. Now we move on the next question. In this question you can see that we know the situation, we do not have to read this one. So this is a situation in which these two capacitors are initially charged, and when they are connected with this cell, then we have to find out the correct option. So in these four options, you can see that first thing which is being asked is the current through the battery immediately after closing this switch and work done by battery. Okay, so let us use a new page. First of all, let us see that this capacitor has a charge Q, which is equal to CV, which is 200 microfarad, and this capacitor has a charge Q2, which is equal to CV, which is 600 microfarad. And the Q total of these two plates, we have connected B and B plates together, so Q total will be minus of 800 microfarad. Okay, so for this connection, let us draw the diagram. And battery is 50 and R is 10. So this is 50 and R is 10. So at t is equal to 0, just after closing the switch, we can see that the potential difference across first capacitor is 100. So this is 100, and the potential difference of the second capacitor is minus 150. This is minus plus plus minus, so this is minus 150. So if we apply KVL like that, so this is minus 50 minus 10i, and this is minus 150 plus 100 is equal to 0. So 10i is equal to 100 minus 200. So I is equal to minus 100 by 10, which is minus 10 ampere. So current in the circuit will be 10 ampere. A is correct. And work done by the battery. So for that we need to draw another diagram. Let us see. that this would be the case. So in this case, you can see that the sum of charges of these two plates should be minus 800. So let us suppose that Q is the charge on this plate and minus Q is the charge on this plate. And this plate, let us suppose that this is capital Q. So this has capital Q minus plus Q, because their sum should be equal to capital Q, and this would have minus of Q plus Q. Okay, so in this case, obviously, we know that at a steady state, the current flowing through the circuit will be zero, and there will be no potential difference across it. So we can apply, and we also know that C is 2 and 4. So this is 2 and this is 4. This is the value of capacitance. We can apply the KVL across this circuit, and I'm redrawing the circuit. This is Q, this is minus Q, its capacitance is 2, and this is Q plus Q, and this is minus of Q plus Q, and its capacitance is 4, and this will be 50. I'm not drawing that resistance. So applying the KVL, we can see that if we are going like that, starting from this point, so minus 50, okay, minus 50, and this would be plus Q divided by 4. Q by C is voltage, and plus Q by C is 2 is equal to 0. So 3Q by 4 plus Q by 4 is equal to 50, and Q we know is minus 800. So 3Q by 4 minus 200 is equal to 50. 3Q by 4 is equal to 250, and Q is equal to 250 into 4, which is 1000 by 3. This is Q. Okay, so this is the final charge on this plate. Now we need to find out the work done by the battery. So work done by the battery is obviously Q flown into EMF of battery. So obviously we know that initial charge on this plate was Q1 200 microfarad on this plate, and Q flown will be equal to final charge minus initial charge. So final charge is 1000 by 3, and initial was 200. So Q flown will be 400 by 3, and work done by battery will be 400 by 3 into EMF of the battery, which is 50. So it would be equal to, this is in obviously micro coulomb. So this is 4 into 5 is 20 into 10 raised to power 3 upon 3 into 10 raised to power minus 6. So this is 20 by 3 millijoules. So the correct answer will be A and C. Now we move on the next question. This question is by mistakenly repeated, so we can omit this one. Now in this question, there is a metal rod like that, and its length is 10x, and this end is A, it is at 0 degree Celsius, and this end is 100 degree Celsius, and there is a point P, and temperature of P is equal to 400 degrees Celsius. It is found that if this point is maintained at this temperature, then the rate of evaporation of water and rate of melting of ice is same, and we have to find out the distance of this point P from this end. So let us suppose that this is y. So obviously we know that dq by dt, which is I1, and this I2 is dq2 by dt. So I1 will be dm by dt, where ice is melting, and that into latent heat of fusion, and I2 will be dm by dt, which is same but latent heat of vaporization for the steam. So I1 by I2 will be equal to 80 by 540, so it is 4 by 27. Okay, so this is I1 by I2, and we know that I1 will be equal to 400 upon the resistance of this part will be y upon Ka, and I2 will be equal to 300 upon resistance of that part will be L minus y upon Ka, and I1 by I2 will be equal to 4 by y upon 3 by L minus y. Okay, and this is equal to 4 by 27. So cancelling 4 with 4, it would be 27L minus 27y, and that is equal to 3y. So 27L will be equal to 30y, y will be equal to 9 by 10 of L. Okay, so 9 by 10 of L means 9 by 10 of 10x. So lambda is 9, you can see. So the correct answer of this is 9. Now let us move on the next question. In this question you can see that there are 5 identical rods which have identical geometry. K is different, and only A and C are maintained at 100 degrees Celsius. The temperature of A is 100 degrees Celsius and temperature of C is 0 degrees Celsius. Okay, and in other words, heat flows in form of A and flows out. Heat flows from A and flows out to C. The temperature difference between ends D and B can be written as 10x degrees Celsius, where x is integer. So obviously we can say that the heat current will be flowing like that only, and it would be same, and there would be no significance of these two rods. So first of all, let us see that RAE will be L upon K by 2A, and R, let's suppose this is 2R, and REF will be L upon KA, which is R, and RFC will be equal to obviously 2R. So R equivalent, these three are in series, so R equivalent will be equal to 5R, and the heat current I flowing through them will be 100 upon 5R, which is 20 by R. Now the potential difference, see, we know that there is no heat flowing through this rod and through this rod, which means that temperature of D is equal to temperature of E, and temperature of F is equal to temperature of B. So if we have to find out the temperature difference between D and B, so TD minus TB will be equal to TE minus TF, and TE minus TF will be I into REF, and REF is R, so this is 20 by R into R. So 20 degrees Celsius is equal to 10x degrees Celsius, so x is equal to 2. So the correct answer of this is 2. Now we move on the next question. Okay, so yeah. In this question, you can see that there is a cylindrical block of length 0.4, area of cross section 0.04. It is placed on a coaxial disc of same cross section, but mass of the disc is 0.4. The upper surface of the cylinder is maintained at a constant temperature of 400 Kelvin, and this disc has an initial temperature of 300 Kelvin, and thermal conductivity of the material of the cylinder is 10, and the specific heat of the disc is 600, and we have to find out the time in which this disc will the temperature of this disc will increase to 350 Kelvin. So obviously at any time t, let's suppose the temperature of this end of the disc is T, and the temperature of complete disc will be same, because it is given that we have to assume the conductivity of the disc to be very high. So let us write down, let us see that what will be the heat current I dq by dt, and dq by dt going in the downward direction will be equal to 400 minus t at any time t divided by resistance R will be equal to 0.4 upon 0.04 into K is 100. In fact, K is 10. Okay. So this is 10. So you can see that R is equal to 1. So this is 1. Now this dq is the heat given to the disc, and dq will be equal to ms dt by dt, and this is 400 minus t. So m is 0.4 and s is 600. Okay, and this is dt by dt is equal to 400 minus t. So dt by dt into 240, because 6 into 4 is 60 into 4 is 240, is equal to 400 minus t, 400 minus t, and dt upon 400 minus t is equal to dt upon 240. Integrating both the sides, this is ln 400 minus t upon minus 1 is equal to t upon 240, and ln 400 minus t is equal to minus t upon 240. The limit of this will be initial temperature of the disc was 300 and finally it was 350. So ln 50 by 100 will be equal to minus t by 240. So this is ln 1 by 2 with a negative sign, t by 240, and this is ln 2. ln 2 will be equal to t by 240, and t will be equal to ln 2 into 240. 240 into 0.693. Okay, so if we calculate this value exactly, 166.32. In this question you can see that this is a battery, ideal battery, and this is connected to series with two resistances R1 and R2, and a voltmeter, which is a faulty voltmeter, when it is connected across this R1, then its reading is 4 volt, which means, and when it is connected across R2, its reading is 6 volt, and when it is connected across battery, its reading is 12 volts, which clearly means that this is the ideal battery, and when this voltmeter would be connected across the battery, then the reading of the voltmeter would be same as the EMF of the battery. So EMF of the battery is 12. Now when this battery is connected with when this voltmeter is connected with in parallel with this R1, so let us suppose that its resistance is R, so its voltage was 4 volt, and obviously the remaining was 8 volt. So we can say that R2 upon the equivalent of R1 and R, which is R1 R upon R1 plus R, will be 2, because the ratio of voltage will be the ratio of resistances. So we can say that this equation becomes R2 by R1 into R, and this is R1 plus R2, and this is equal to 2, first equation. And in the second part, if you can see that when this is connected across the second one, then this is R1 and this is R2 and this is R. Then the voltage across this is 6, which is, this is also 6, which means that R1 is equal to R2 upon R1 plus R2. Okay, because these two will be same. So we can say that by these two equations, this is second equation, and we can use that R2 by R1 into R is into R1 plus R2 into R1 plus R2 is equal to 2. This is equal to 2. Okay, and if we multiply these two equations, we can say that 2R1 multiplying 1 and 2, 2R1 is equal to R2 into R2 by R1 into R, cancelling R with R. So 2R1 square is equal to R2 square. So R1 by R2 will be equal to 1 by root 2. So if we wish to find out the original voltage across R1, so if we can assume that R2 is equal to R, then R1 is equal to, or what we can do, we can divide the voltage in this ratio. So this is R1, this is R2, ratio is 1 by root 2. So the total voltage is 12 volts. So one part, the voltage on this V1 will be the original voltage on R1. We have to find the original voltage across R1. So V1 will be equal to R1 upon R1 plus R2. So it is 12 into 1 upon 1 plus root 2. Now 1 plus this would be 12 upon 1 plus root 2 is 2.73. Root 2 is 1 point, in fact root 2 is 1.414. So this is 2.414. So 12 divided by 2.414 is 4.97. So this is 4.97 volts. So the correct answer will be 4.97 volts. Now let's move on the next question. In this question, there are three rods AO, BO, and CO having equal length and equal area of cross section. They are connected like that. The temperature of end A, B, and C is 30, 60, and 90, and the thermal conductivity are in the ratio as shown. So if this is K, then the thermal conductivity of BO will be 2K and will be of CO will be 3K. So what is the temperature of junction? So temperature of A is 30, temperature of B is 60, and temperature of C is 90. So let us apply the nodal. So TO minus 30 upon RA. Now R is same, in fact length and area is same. So we can multiply with K plus TO minus 60 into 2K plus TO minus 90 into 3K is equal to 0. So this is TO minus 30 plus 2TO minus 120 plus 3TO minus 270 is equal to 0. This is 6TO and it is equal to 420. You can see 30 plus 270 is 300 and 120 is 420. 120 plus 300 is 420. So this is 70 degrees Celsius. 420 by 6. So the temperature of junction is 70 degree Celsius. This is the correct answer. Thank you.